Hey everyone, I'm Prajit from Buster Lab at Imperial College London. Today I'm going to talk about X-node, self-explanation is all we need. This part of the research is on explainable graph neural networks, particularly for medical AI where trust and interpretability are very crucial. So, let's say we have Dr. Sarah who wants to know whether a X-ray or MRI scan of a tumor is a malignant or not. And the AI says, yeah, it's a malignant tumor with 95% accuracy. And then she's inquisitive and says, why? Why do you predict so? Why it's a malignant tumor according to you? And obviously the AI says silent because whether it be a CNN convolution neural network or any other neural networks or even GNN graph neural network, backpropagation, message passing, a lot of things happen. But we don't exactly know why it's happening, and obviously it doesn't say to us why it's predicting in such manner. So we have three problems. First, black box decisions. Second, no clinical trust. And third, no human language, most importantly. So how do we solve this? Before diving into this, let us understand some of the explanation methods which are partially trying to address this issue. GNN explainability is divided into two parts, anti-hoc, post-hoc. Post-hoc is after training, anti-hoc is during training. Anti-hoc has a part which is known as self-explaining GNNs. There are a lot of types of self-explaining GNNs like GNN LRP, prototype GNN rage. And post-hoc has three types: feature attribution, subgraph extraction, and counterfactual explanations. Let's go one by one. Self-explaining GNN, these GNNs they generate the predictions and explanations for transparent decision making. So it's a whole GNN for which the prediction is driven for. To post-hoc and feature attribution, it tells us which features matters the most during a prediction. So extraction highlights which part of the graph influence the prediction. It might be a different topology of the graph which influence the prediction. For a different prediction, it might be a different topology. And interestingly, the counterfactual explanation tells us how changing certain parts would alter the prediction. Like if you put a bit of the input, how it affects the prediction. And now we dive and introduce you a very new field in anti-hoc, which is the explanation of a training. So what is explanation of a training? It incorporates explainability into the training process to enhance the model's reasoning per node. So the self-explained GNNs in the anti-hoc one were for whole GNN, but here we want to do the explainability per node and the reasoning over it. And this is where we introduce our method X-node. So all these existing methods struggle to provide clear node-specific explanations that align with clinical reasoning. And there our X-node comes into play, where it enables each node to generate the clear tailored explanation for that node, and which is integrated into the training process, and there is a reasoning happening over the explanation to further improve it even if there's some wrong. So let's move from problem to solution. So for example, we have a medical image dataset which goes into, for example, a GNN neural network, and during training, and it gives us a prediction y-hat. So we don't exactly know why it is predicting this y-hat at the end of the day, and that's exactly what we want to understand. And there might be message passing or something, but all these GNNs, they predict currently and they are not explaining it. And we need, apart from y-hat, an explanation attached with it, why it has predicted y-hat at this moment. So let's focus on two nodes here, node 1 and node 3, and let's zoom into that. So there's node 1, it's representing one organ. There is node 3, and our vision is like they talk to each other, they self-explain to each other that these nodes are explaining, okay, I'm doing this. So they're connected with an edge, and for example, node 1 says, hey, I'm lung right, I'm fairly confident, and turn out I was right. And then node 3 says that it had made a prediction of kidney right, and it wants to reflect why it has chosen such a label. And then they both dive into their topological features. For example, they both are talking about the degree. The node 1 is talking about degrees 12, the node 3 is talking about the degrees 2. So they both are trying to reason about some of their features. Then they dive into more features, maybe like clustering coefficient, and then dive further into more features, just like maybe 2-hop neighborhood. And this way, they reason all over it and try to understand that why they have chosen a particular label compared to the neighbors, or maybe their degree or clustering coefficient. And at the end, for example, if you see node 1, they conclude by saying, it was likely that a big influence on my prediction, and I was basically surrounded by nodes that said, hey, I'm a lung right too. That's why I predicted lung right. So they first say what they're predicting, explains it, and then they are concluding that why they have made the prediction, which builds the clinician trust. And this is what we want to attain at this end of the research. So the overall architecture of this is that we have multiple steps, and we'll go through each step one by one. First step, graph construction. So we have a medical image dataset. From this whole dataset, we take a particular image, for example, like XI, and obviously there is an associated label with it, YI, that will link to the dataset. This X is converted into Fi, that is, we vectorize all those PNG of each image into a vector, and each node is representing a particular image. Then with each Fi, we find a cosine similarity between Fi and Fj, and we take the top k and create the edges. And that forms our adjacency matrix. And bingo, we have our graph with vertices, which are the nodes, the edges, adjacency matrix, and X are the features of the nodes. The second step we are with the context vector magic, which is really very important to this paper. For example, let's take node 3. From the node 3, we can extract a lot of things like average, weight, clustering coefficient, degree, between centrality, 2-hop. These are all topological features. So how we are extracting topological figures, just because if you remember, we just converted the medical images into a graph altogether. Since it's a graph, it has neighbors, it has edges, so we can extract such topological features from it. These topological features are defined as follows. They are mathematical statistical properties. We calculate them, and all these calculations are then put into a context vector Ci and concatenated. Later, this context vector goes into a frozen LLM, which, if you remember, when the nodes were speaking to each other and saying they're predicting lung right, they are explaining from these features itself. So degree, clustering coefficient, 2-hop neighbors, all these numbers come from this context vector at the end of the day. Next, we move into reasoner. So it's just not that we want to explain what a node is predicting, but we also want to improve the performance of explaining. So if it's saying that, hey, I've predicted wrong because of these reasons, so we can go back and then we can backpropagate and improve it further. So that's where reasoner comes into place. So the context vector which we have, it goes into a simple reason MLP, which has two trainable weights W1, W2, and two biases P1, P2, and it outputs an explanation vector, which is nothing but a distilled summary of the node's reasoning, capturing only the essential factors which are driving prediction. So it might be like 6 topological features goes into a context vector, and there's an explanation vector which comes out, which is just concentrating on the important features, and this is used in the downstream tasks. Next, we have the ensuring faithfulness and text injection. That explanation vector comes into the decoder head, and we reconstruct an embedding which is H-I. This H-I is compared with the original embeddings of the GNN. It can be any graph neural network, it can be a GCN, it can be a GAT, and then that forms our reconstruction loss. Further, that EI explanation vector is also concatenated with the original embedding just to further enhance the embedding, which is the ZI, if you notice here. And this ZI goes into MLP class and predicts Y hat I. This Y hat I is a enhanced version of prediction. So this prediction is more of that how better to improve the prediction is compared to a normal YI. So at the end, we have 3 losses. One is the classification loss, one is the alignment loss, and one is the reconstruction loss. So here overall in this slide, we truly understand how, with the help of the context vector, when we decode it back, we reconstruct the embedding, we try to find that those topological features, which is more important, focus on those and then make the prediction instead of just creating an embedding overall just by message passing. And this way, we are increasing the performance further. The last stage, text generation. So to generate a text, we obviously need a prompt for explanation, and our prompt goes like this. You are a node in a medical graph. Your topological context is a context vector, which is this. If you remember, we just create a context vector. Just to note, this context vector is like a dictionary, key and value pair. So a key would be degree, value would be, its value is like 0.2. Clustering coefficient, 5, something like that. Your predictor label would be a label, true label. Explain in natural language why you predicted such label. If incorrect, then tell us why it is misled based on your structured feature and labels. So this way, we self-narrate the decision logic, but also if the predictor label is a wrong one compared to true label, it also introspects its own failures. Let's go into some examples. This is a false prediction example where the true label is kidney right, but it predicted false. So it starts by saying, okay, my femoral class, which is a true label, my true label is kidney right, but I rated femoral left. And it starts moving into like my degree is 4, maybe my clustering coefficient is 0. Okay, that's why I understand that my neighbors are not very well connected to each other. And also there could be the high average edge weight could be a cause of error, because obviously 0.929. And all these things and all these stuff are overridden by all my misleading neighborhood influence. And at the end, it tries to conclude that this misclassification reveals how the structural signals can dominate the node identity. So if you see this, it has tried to explain why it had predicted a wrong manner, and in this way the clinician can have trust, okay, this is the reason it predicted wrong. Let's next time we just keep these things in notice before running the GNN or any other neural network. Let's go into true prediction. For example, here it was fairly confident that it's predicted right, and it thinks that its topology had a lot to do with degree was dual where cluster not just 0, but it's quite low, but its true hop percentage was quite high. So its neighbors were of 96% connected to each other. Since it has so high 2 point percentage and all were lung, that's why it predicted it was lung, right? Which makes really sense, and okay, and even the clinician would be like, okay, I believe this. So the experimental setup, we have 6 data sets. 5 of them are from MetaMNIST, which is lightweight standardized data sets, and 1 is from MorphoMNIST, which is an extension of MNIST that adds morphological attributes like shape-based variation, like thickness, thin, broken, text like that. This is just to increase our generalization of our model to understand how well it generalizes. So the node counts from 7K to 236K, label ranges from 4 to 11 classes, and we have done all the experiments across 3-fold cross-validation setup. Computation over analysis is a very important thing. If you notice, adding a reasoner increase epoch time and memory only moderately. So it's like, for example, in organ AMNIS, it increased from 1.15 to 1.78 compared to the benefits we are gaining. And also, the memory consumption decreases for large-scale graph like tissue-MNIST and morpho-MNIST are quite large-scale graph, and the memory consumptions in this, if you notice in tissue-MNIST, decreases from 2472 to 1781. It's just because we are telling in the reason that concentrate on particular topological features and not everything else. So when we are making it concentrate on a particular one, automatically its memory decreases, memory consumption. Performance, 1-2% increase across all data sets and all of our metrics. Accuracy in large graphs like tissue-MNIST, morpho-MNIST decreases a bit. Yes, not highly, but it decreases a bit. But the sensitivity across all the graphs, if you notice, whether it be large-scale graph, it increases from 3 to 5%, which is more important parameter in medical domain. And F1 score also increases 2 to 3%. So compared to existing methods like GNN explainer, RAGE, PZ explainer, you notice XNode ticks all the things which you really want. It's intrinsic, it's node-level explanations, it has a feedback loop, and most importantly, it gives a human language understanding or explanation to the clinician or people who are not technical. So conclusion, strengths of our model, intrinsic explainability, explanations are part of the learning and not afterthoughts. Local topology reasoning, which is very important for medical patterns because there can be, if they're connected to each other, this means they're close to each other, organs might be close to each other, there's some similar patterns between them. Certain research directions which we can move into is LM and prompt variation, obviously different models they can try out and with different ways of reasoning, different prompts. And more importantly, I think we can explore more features. I have just explored here 6 and 7 features, we can explore, try out with different features. That's it. Thank you so much.